AP Calculus AB, another particle motion question off of an exam. So I thought we'd look at this. I just want to say again that these questions have shown up about 95% of the time over the last 10 years on AP Calculus AB exams. This comes from a 2006 Form B exam. So here we have this. It says a car travels on a straight track during the interval t is greater than or equal to 0 and less than or equal to 60 seconds. The car's velocity v is measured in feet per second. The acceleration a measured in feet per second are continuous functions. The table above shows selected values. So this is what we're going to do. It's going to start picking this thing apart, right? Be careful that we have really looked at this. This is velocity, this is acceleration, and this is time. We don't have a position function here. So it says for A, it says using appropriate units, explain the meaning of the definite integral from 30 to 60 of the absolute, look at this carefully, of the absolute value, right? Absolute value of v of t dt. So one thing I'm going to do is I'm just going to start here and say, you know what, here's what we're looking at right here. So they're asking us what, right? They're saying to tell us what this means. Well, what does this mean? Absolute value means it doesn't matter if it's moving left or right, right? We just want distance. So this is distance. So I'm going to jump over to my paper. I'm going to label this thing A and say that I'm going to repeat the question a tiny bit to them, 30 to 60 of absolute value v of t dt is the distance, because that's what they're looking for. They're looking for that word distance. In feet the car travels. In feet the car travels. So that's A part 1. Then we have A part B. And A part B says that they ask us to use, what is it? It says approximate that function using a trapezoidal approximation. So let's look at this for a second, just what they're saying. So they ask us to use, this is really important too. Keep in mind they want us to go from 30 to 60, and they want us to use a trapezoidal approximation with 3 subintervals. So this is what we're going to do. If you can look at this. Here's the first subinterval. Here's the second subinterval. Here's the third subinterval. Here, the change of x is equal to 5, isn't it? Here, the change of x is equal to 15. And here, the change of x is equal to 10. You see what we're doing here? So, because we don't have even subintervals here, this is just representative data. We don't have a function to work from, so we're forced inside the table. So, this is what I'm going to start doing. Right? What you're going to do is keep coming back to this table, but I'm going to take this table data. I'm taking this data, this data, this data, this data, right? So the first interval is this one to this one. Remember that it's absolute value, so I'm going to have 14 plus 10. Then I'm going to have 10 plus 0, and then 0 plus 10, right? So let's just put this into trapezoidal form. So the first thing I'm going to do is say that d is equal to 1/2, right? And if you look at the table, you see it says negative 14 to 14, but it's 14 plus, I'm sorry, it's negative 14 to negative 10, but it's absolute value here. So we have it this way. If you remember the distance between the two, the change of x in the first one was 5, wasn't it? Then I'm going to do the second one, which is 1/2. And if you remember, it was from negative 10 to 0, so it's 10. And if you remember that the change in x there was 15, and then I'm going to do the last one, 1/2, and it was 0 to 10, so 10 again, and the change in x was also 10. And then I'm just going to I'm going to use my calculator and put all of this stuff together, right? We are not forced to cram out this arithmetic. I want to show them that I'm using this rule, right? I want to show them that I'm using this trapezoidal rule. So here's my example of using the trapezoidal rule, and now I'm just going to write the answer. And if you did all this arithmetic, you'd get 185. Please remember to use feet. So I have this answer here for A, and this answer here for A. That's all of A. Then I'm going to go back and I'm going to start section B of the exam, right? You're going to have about 15 minutes to do this. So everything is cool. You have plenty of time. There's no need to freak out. Everything's going to be fine. Go back to B. So first off, we did that, right? So using appropriate units, explain the meaning of 0 to 30 of the definite integral 0 to 30 of A of t dt. So we're looking at A. What's A all about? In terms of the car's motion, find the exact value of this, right? Find the exact value of the definite integral 0 to 30 of A of t dt. Not hard at all, because it's just, right? This is a derivative, so this is the change in velocity. This acceleration is change in velocity. So we're going to say change in velocity from t equals 0 to t equals 30. No problem. T equals 0 to t equals 30. I'm not overthinking it. I'm not overthinking it. What I do want to write is some good calculus for them, so I want to write that it's 0 to 30 A of t dt, I apologize, A of t dt is 0 to 30, right, of v prime at t, right, because v prime at t is A of t, isn't it? Right, because the first derivative of velocity is acceleration. So it's equal to v of 30 minus v of 0 which is negative 14 minus 20. Which is only 6 feet per second. So this one was really, really easy, I think. And right, I'm writing my calculus, and I'm using, I don't even need to use a calculator here. So here's part B. Hopefully that made good sense to you. We're getting there. Look, I bet we're not 5 minutes into this, and we have 15 minutes to get this done. So knowing kind of what we're going to do next is going to be the most helpful. So we have this done. It says for t is greater than 0 and less than 60, must there be a time when when v of t is equal to negative 5? Justify your answer. So does it ever have to go to negative 5? Well, yeah. Can you see where it does? Right. Remember, we have intermediate value theorem. Right. Intermediate value theorem. So what I'm seeing is this. Right here. Can you see it? Because look. We're in velocity, and here velocity goes from negative 10 to 0. If the velocity goes from negative 10 to 0, it had to pass through negative 5. Right? So this is how I would answer this question, I think. I would write C at t equals 35, v of t equals negative 10. At t equals 50, v of t equals 0. So we can say that it has to go from negative 10 to 0. And all I'm saying is that these things are in between each other, aren't they? Right? So here's my proof. And I would definitely write intermediate value theorem. You can write it just like that. This will mean a ton in your grade to quote intermediate value theorem here. And it makes perfect sense to me. But you have to show something. And this, believe it or not, is very good justification. So let's go back and look one more time at the very last question. So we got question C done. Question D says, for t is greater than 0 and less than 60, must there be a time, t, when the acceleration is 0? What I always do is, excuse me, when I look at questions like this, I ask myself, is there any time when the velocities are the same? That's what I'm looking for. I saw that question. I'm like, I wonder if there's any time the velocities are the same. And they are. They're the same here and here. So if the velocity here is negative 20, and the velocity here is negative 20, and it went to negative 30, right? Then didn't the acceleration have to go to 0 at some point, right? It's the derivative, right? So here we have the point 0, negative 20. We have the point, this is really weird. I look at it like this. 0, negative 20. 25, negative 20 is this point over here. And somewhere down here is the point 15, 15, negative 30, right? So this thing does, the velocity does this. So isn't acceleration the derivative of velocity? And if the answer is yes, then doesn't the slope go to 0 here, right? Doesn't acceleration have to change, right? So that's how I would answer that question. I'd say, okay, yes, D. Say yes. V of 0 is equal to, was it V of 25? Of V of 25. Yeah, I used Rolle's theorem. The book, the scoring guide used mean value theorem. It doesn't matter. You can use either one, but it guarantees that these things are the same. So mean value theorem, A of t. Look, this is, let me say this. V prime at t, the derivative of velocity, is acceleration. And if this thing went from negative 20, the velocity went from negative 20 to negative 30 back to negative 20, then it had to change directions, didn't it? And for it to change directions, it has to have a slope of 0. So A prime at t equals 0 at least once. At least once. Okay? And that's what they're asking us. And this is my answer. Make sure you circle your answers. Yes. Okay? Look, you guys, I hope this is helpful. We can definitely do this. I'm going to be doing a ton of these videos and actually having some students produce them also to see if we can get a huge number of them. I want you to look at them. I want you to look at them carefully. And I also want to make sure that you're looking at area and volume questions because they show up almost 100% of the time also. All right, you guys? Hey, thanks for watching. If you have any comments, please let me know. And if you haven't already subscribed, please subscribe. Thanks.